As we begin with the topic of differentiation, let us understand the concept of what is called as derivative of a function from the geometrical perspective. Now, just to give you a little background, the process of finding a derivative was motivated by trying to find the slope of a tangent to any curve at a given point. So, that was a challenge which evolved into this particular topic of differentiation. So, let us consider some general curve. Say this is the curve of some function. Let's call it as, say, f of x. Right? And at some given point, let's consider this is that particular point. We want to find the slope of the tangent. So that means if I draw the tangent, it looks like this, and we are interested to know what is the slope of this particular tangent drawn at this particular point. Okay. Now let us denote in general the point as, say, a. Okay, so the value of x is, say, a. Now if that is the case, the point on the curve, let's call it as, say, point A. We know that the x coordinate of point A is small a, and hence its corresponding y coordinate will be f of a. So these are the coordinates of point A. Now, in order to find the slope of this particular tangent, what do? Is we start off with a crude approximation. That is, we consider some point far away. That is, let's consider this particular point, let's call it as point B. And this particular point B is situated at some distance away from A. So if we drop a perpendicular on x-axis, let's call its x coordinate as, say, a plus h. So in other words, the difference between their x coordinates is h. Right? Now if we see the coordinates of point B, its x coordinate is a plus h. So therefore obviously its y coordinate will be f of a plus h. Alright. Now if you look at line AB, which is nothing but we can call it as a secant AB because it cuts the curve in 2 points A and B. Right? Now can we write the slope of secant AB, that is slope of secant AB is equal to, we know that by the formula of finding out the slope, that is y2 minus y1 upon x2 minus x1. Let's call first point as A and second point as B. So therefore slope of AB turns out to be f of a plus h minus f of a whole divided by a plus h minus a. So that is nothing but f of a plus h minus f of a, and in the denominator a will get cancelled, so therefore we are left with just h. Right? So that is the slope of secant AB. Now is this the slope that we are actually interested in? Obviously no, because we want to find the slope of tangent at A. So what do is we now consider some point which is slightly closer to A as considered from the perspective of B. So it's like point B is moving on the curve towards A. Right? So because of this, what happens is the new secant will look something like this. Now I hope you are able to imagine that. What happens is now the secant becomes slightly more tilted, and now that is bit closer to the actual tangent. And in this process what happens is the h gets reduced to a further smaller value. So now you can imagine that if we go on reducing h, ultimately in the limiting condition when that h tends to 0, the secant AB will eventually approach and become the tangent at point A. Alright. So therefore the slope of tangent is nothing but the limit of the slope of secant as the quantity h reduces and approaches 0. So therefore we can say that slope of tangent at A is nothing but, we know that it has to be the limiting value of the slope of secant. So therefore we have to find the limit of slope of secant, which we have just found above, is f of a plus h minus f of a whole divided by h, and we take the limit as this particular difference h tends to 0. Alright. Now this particular quantity that we have obtained at the end, it represents the slope of tangent at A, and that is what is the concept of derivative. So this particular limit is called as the derivative of the given function, that is f of x, at a particular point which is x equal to A. Right. Now that is because, why we have to specify the point is because if I just say that find out the slope of tangent to some curve, obviously the question is at which point, isn't it? So to draw a tangent, we first must know at which point we have to draw the tangent. So therefore we have to remember that the derivative of any function is always defined at a particular given point. Okay, so let us go ahead and now just recap the formal definition of the derivative of a function. So the definition of derivative, which is also called as the first principles. The derivative of a function f of x is defined as f dash of x is equal to limit of f of x plus h minus f of x whole upon h as h tends to 0. So this f dash of x is the symbol for the derivative of f of x. Okay. Now the definition which we have seen, it is a very general definition in terms of x. If we want to find the derivative of f of x at a particular point, at a given point, say x equal to a, then we have to simply replace x with a in the above definition. So therefore we write it as f dash of a is equal to limit of f of a plus h minus f of a whole upon h as h tends to 0. Okay. So whenever we are asked to find the derivative of a function using first principles, we have to basically evaluate this particular limit shown. Okay, let's move ahead to the next. Now here remember that we have to understand the wording, that is a function f of x is said to be differentiable at x equal to a provided its derivative at x equal to a exists. That is the limit of f of a plus h minus f of a whole upon h as h tends to 0 exists. So, so that just means that a differentiable function means that its derivative exists at a particular point. Okay. Moving ahead. Here we have additional notations for denoting the derivative. Now here it is the Leibniz notation for derivative. That is, if y is some function of x, say f of x, then dy by dx denotes the derivative of y with respect to x. So in other words, dy by dx is nothing but limit of delta y upon delta x as delta x tends to 0. Okay. Now let's understand from where this comes. It is very much similar to the original concept that we saw using the geometrical perspective. So let's consider a curve of some function. Okay. Now here we consider 2 points, if you remember, a and b. Now the tangent at point A looks like this, right? And the secant joining the points A and B is like this. Okay. So now if we complete the triangle by drawing the perpendiculars horizontally and vertically, we see that the difference in x coordinates of a and b is nothing but delta x, correct? And similarly the difference in their y coordinates is nothing but delta y. And therefore we know that the ratio of delta y upon delta x is nothing but simply the slope of secant AB. And therefore as the quantity delta x becomes smaller and smaller, the slope of secant will tend to the slope of tangent in limiting condition. So therefore this is just a different notation for the derivative. In fact there are few more notations as given in the last note here. That is, there are other notations also for derivatives, namely f dash of x is same as dy by dx, that is also denoted by y dash, so the dash represents the derivative, and sometimes that is also denoted by y1, so that stands for the derivative of y evaluated for the first time, so that's called as the first derivative. Right. Now just one more point to make clear, that this dy by dx, obviously here we cannot say that d is to be cancelled because d is not a variable in itself. Okay. The dy by dx actually means that the derivative of y with respect to x. So that means dy by dx stands for d by dx, which is called as the differential operator, and that operator operates on the variable y. So that means it is d by dx of y. Okay. So that is a clearer meaning of the Leibniz notation. Now based on this we will solve few examples on how to find the derivative using the first principles, that is the definition of derivative as a limit.